Follow along with me to make your first project for the real-time target. Here's what we're going to make. We'll create a VI to run on the real-time target to blink the onboard LEDs. This will also serve as the startup VI for the academic Rio device. We'll also create a human-machine interface running on the desktop computer to interactively control the VI on the real-time target. We will use the default FPGA personality and associated academic Rio Toolkit Express VIs that run on the real-time target. We'll build this application in 5 steps. We'll begin by creating a new LabVIEW project, creating and deploying shared variables between the desktop computer and the real-time target. We'll create the VI that runs on the real-time target, and then the VI that runs on the PC desktop. And finally, we'll set the real-time main VI as the startup VI. The completed LabVIEW project is also available for download. Alright, let's begin by creating a new LabVIEW project. I've just started up LabVIEW. Select File, New, and then choose Empty Project. Save the project to a folder that will contain all of the files associated with this particular project. I'll call this project First RT Application. Next, let's add an academic Rio device. I'm going to discover an existing target, and in my case I have a MyRio attached. I'm going to illustrate how you can rename the device if you like. I'll call this NI MyRio 1900. For a project that does not require custom access to the FPGA, you might wish to just delete the chassis altogether. If you change your mind at some time in the future, you can always get this back. And again, this is the MyRio chassis. Next, let's create and deploy some shared variables that can be used to establish communication between the real-time target and the desktop computer. I've selected my target and say New Variable. And the first variable that I'm going to create is a Boolean called LEDA. You see it's been created under a default library name of Untitled Library 1. You can then create subsequent variables by selecting the library, giving the appropriate names, in this case LEDB, and this is also a Boolean. You can also create variables all at once. This is using the batch variable creation tool. Base name, I'll just go with variable. Let's select the data type as Boolean. I want to create 4 of these all together. You could also take the option of copying the properties from an existing variable. For example, we could take it from LEDA. And we'll go with this default that says display the multiple variable editor window after creating the variables. And we see the 4 variables that have been created. Let's go and adjust their names and so on. First one I will call pause. The next one is paused with a D. Third one is stop. And the fourth one is called loop time with units of milliseconds. Now the meaning of all these variables will become clear here just very shortly. Loop time needs to be an unsigned integer 32-bit. Alright, there we see all 6 variables have been created. The asterisk indicates that the project has not been saved lately, and I'll go ahead and save it, and then I'm also prompted to save the newly created library, and I will call this First RT App. Alright, a couple steps to deploy these variables permanently. I'll begin by registering this device. 172.22.11.2 is the IP address of your academic Rio when it's connected by the USB LAN. Then we select Deploy All to make these variables persist even across power cycles of the device. Let's take a look at the Distributed System Manager. We'll look under the IP address, and there's the library, and here's the variables. This is a very handy tool for setting values of the shared variables as well as inspecting their values at any time. All right, let's continue on by creating the VI that will run on the real-time target. Select your target and then New VI. I'm going to save this as RT main. And I like to right away edit the icon with the same name as the VI. This makes it easier to identify the VI, especially when you have multiple VI windows open at once. Let's use the tile left and right mode to see the block diagram and the front panel at the same time. I'll begin by placing a flat sequence structure. Let's open a second frame. And in the first frame, I want to initialize some selected shared variables. First one is loop time. At the moment, this is read access. We need to change the mode to write. Then I can create a constant. Let's initialize this to 100 milliseconds. Let's open up a subdiagram label, and that's a handy way to put in some comments on your sequence structure. Let's grab the pause shared variable. Access mode again needs to be write, and we'll initialize that one to false. My third variable is very similar. I'll select this, hold the control button down, and then click and drag. Select the stop variable, and then we're done. All right, let's open up and pin the subpalette for the MyRio Toolkit Express VIs. And these will be useful for accessing the onboard resources via the default FPGA personality. We have the onboard button. A Boolean true from either the button express VI or the pause shared variable will cause the blinking to pause. So we'll connect these two together with an OR function. I'm going to use the feedback node as a memory element as the basis of the LED blinker. This is a little bit easier to work with when we change its direction. The exclusive OR gate will serve as effectively an inverter with an enable input. And when this is wrapped inside of a while loop, that will oscillate back and forth between false and true states. Now let's access the onboard LEDs. Let's make use of LEDs 0 through 2. LED 0 will be the primary blinker output. LED 1 will be the opposite of that, or the complement of that. And LED 2 will indicate the paused state of the blinker. So we'll wire that one back to the OR function output. Let's do just a bit of rearranging here. Tighten up some space, and let's open up some space right there. And I'm going to place a shared variable for each of these three LEDs. So we have LED A, and we'll need LED B. And then one more copy for the pause indicator. All right, that looks pretty good. All right, let's wrap this inside of a while loop. And later I'll be adding a second process loop. We'll call this one process loop number 1. The loop iteration time will be controlled by the shared variable that we created earlier. And we'll use the stop shared variable to stop this loop. It's generally good practice when the VI shuts down that any I/O devices you have be brought back to default or inactive states. So we have our main process to blink the LEDs, and then as part of the shutdown sequence, we'll cause all of these LEDs to go to their inactive states. All right, that takes care of process loop number 1. We had the initialization step, the process loop body itself, and then the shutdown sequence. Let's place one more process loop. This one's making use of the timed loop structure. And this one will simply blink LED 3 at the rate of 1 Hertz, or 1 blink per second. We'll use the same oscillator structure as before, but this one has no need of an enable, so we'll just use a not function for that purpose. We'll use the same stop shared variable to stop this loop as well. And I would also like to shut off this LED when the timed loop stops. Let's call this process loop number 2. And here's where we can adjust the loop timing. Double click on that and choose a 500 millisecond period. The LED will be on for 500 milliseconds and then off for 500 milliseconds. The free text labels are a great way to add documentation to your block diagram code. All right, go ahead and save that. VIs that are intended for the real-time target rarely have front panel controls and indicators, and for this reason they are referred to as headless VIs. I will place a label, however, so that way we can recognize something when the VI is opened up for the first time. Let's go ahead and save that, and I think we're ready to give this a try. LED 3 is blinking as expected, but LEDs 0 and 1 are not. Let's try manipulating some of the shared variables. In particular, let's try the pause function right here. Okay, when that's true, then it blinks, and when it's false, it does not blink. So it looks like that's operating backwards from what I had intended. Looks like the trouble spot is right here. That should have been a NOR function instead of an OR function. Let's just stop that and insert some space here. I think what I'll do is insert a not function right there. And that way we keep the existing functionality of the paused indicator. Let's try this again. All right, blinking right away. And again, let's try some of our shared variables. So we'll try setting the pause, and it pauses. That looks good. Let's try pressing the onboard button. So I'm holding it down right now and it's paused, and let go. And we're back to blinking, so that we've got a pause from either the shared variable or the onboard button. Let's try varying the blink rate. All right, longer loop time means it blinks slower. Let's try a quicker one. Looks good. Let's set this back to 100 milliseconds. All right, that seems that everything's working properly. Let's see whether or not we can stop the VI. And that also works. All right, our testing and debugging process of this VI has been a success. Let's move along to creating the human-machine interface that runs on the desktop computer. Select My Computer and then New VI. And let's edit the name in the icon. Call this one PC Main. And let's get started on the front panel. Going to create a Boolean push button for pause. We'll need 3 Boolean indicators for the blinking LEDs as well as the paused state. I'll use the horizontal pointer slide to set the loop time. For this control, we will need a unsigned integer 32-bit, minimum value of 10, maximum value of 1000. We'll go with logarithmic mapping style. The digital display lets you key in a specific number, and let's save that value of 100 milliseconds as the default value. I have one more Boolean push button. This one looks a little bit different. And I'll be using this one as the button to stop the VI running on the real-time target. Again, HMI stands for Human Machine Interface. And let's tidy up the appearance of the front panel. All right, let's head back to the block diagram. All of these front panel controls and indicators simply need to be in their own place on the block diagram. They do not connect to anything. Or that is, they do not connect to anything on the block diagram itself. Instead, these controls and indicators will be bound to the shared variables that we had created earlier. I notice that the PC VI has not yet been saved. Let me go ahead and save the entire project and then give that VI the name PC Main. Now, right-click on the control, find the tab for data binding. We'll use the shared variable engine, and then browse to network items. There's the IP address, there's the library, and we'll bind that to loop time. And we only need to write data to that. Notice the little flag now has been added, and that's our indicator that the control has been bound to a shared variable. Now you could repeat this process for the remaining 5. However, I'll show you another way to do this. With this tool, you can more conveniently see how you've got all of your variables set up for binding. Now this is kind of familiar to when we're using the interface through the tab. But again, it does have the advantage that we see everything more or less all at once. Now once you get the idea, I'd invite you to go ahead and finish this off yourself. I'm going to jump ahead here a little bit. And then we'll hit apply. And we see the little flag has been attached to every single control and indicator. Now, the rest of the block diagram is pretty simple. I just need to have an idle loop that does nothing except wait for the stop button to be pressed. The idea is that the VI principally is just working with the bound front panel controls and indicators, and this little structure with the idle loop will keep it running until we press stop. I'm going to use the event structure based on the stop button. Need to move that inside. And here we have a very CPU efficient method for doing nothing except checking to see if the stop button has been clicked. Well, let's give this a try. I'll begin by running the VI on the real-time target. And then let's start the VI running on the desktop. Note that all of the binding indicators are green, and that tells you that they are successfully talking to the deployed variables. Okay, the pause function works. Let's try the loop time. All right, again, so the idea here is that we have a nice friendly user interface to manipulate through the network connection to manipulate the behavior of the VI running on the real-time target. So again, this is still running on the real-time target. We haven't stopped that one yet. So taking a look at the distributed system manager, again, just trying to drive home the point here that when you manipulate these bound variables, you are directly manipulating these shared variables. Now, of course, we can see that the real-time VI is still running, and we'll click stop. That sets the shared variable, which then causes both process loops to shut down in the real-time target. All right, let's wrap things up by setting the RT main VI as the startup VI. This way it will run every time that you power up or reboot your academic Rio device. We'll right-click on Build Specifications, and we want a new real-time application. I'll just go with the default name for that, and we can stick with the defaults for everything else on that page. We designate RT main as the startup VI and click Build. This compiles the block diagram and generates all of the necessary files to deploy on the academic Rio device as the startup. We'll then right-click and choose Run as Startup. We'll go ahead and do the reboot as suggested. You will likely need to enter your admin credentials at that point. This process takes a little bit. You'll see the status indicator goes orange as part of the reboot process. And then when you wait a little bit longer, you'll see that the real-time VI automatically starts running. I'll run my desktop remote control. Check that out. That all looks good. Okay, behavior's checking out fine. And when I stop the VI on the desktop, then the VI on the academic Rio device keeps going, of course, until you press stop, and then that shuts down the VI remotely. Well, congratulations, you have just completed your first real-time application.